Okay, so today we are going to start our bipolar junction transistor lecture again. We talked about several things in the past. In BJT section, we talked about the basic principle of operation. We looked at the semiconductor physics of the transistor and also the operational modes of the BJT, basically the cutoff region, active linear region and saturation region. We said depending on the number of forward bias junctions in the BJT, there will be three such things. And we then looked at the transistor characteristics, the output characteristics, the relationship between IC and VCE. When the third, there was a third variable also, IB. When IB changed, how each of the IB, when IB changed, how IC changed with VCE. So we looked at it, and there also we identified three different regions: the cutoff region, active linear region, and the saturation region. In addition to the high power region where you have the too much energy dissipation, so therefore which is called the breakdown region. So that was another region. So we had that. We also looked at the input characteristics very briefly. We said it's just the same as the diode. Okay, and today we are going to talk about biasing a transistor. So today's lecture is basically about biasing a transistor. Okay, today we are going to look at biasing a BJT. So what is biasing? Let's see. To understand that, let's take a small circuit. We have a BJT NPN type transistor. We connect the emitter to the ground, and the collector is connected to a battery through a resistor RC. Let's say this battery voltage is VCC. And we want to see what happens to this if I connect a pure sinusoidal signal to the base through a resistor RB. So this Vin is a pure sinusoid, and I'm connecting it to this. I want to see what is the output VCC at VC, which is V out. Okay, so let's that this is the base, this is the collector, this is the emitter, this is the base emitter voltage VBE. If this transistor was conducting, this would be 0.7. If not, we don't know the value. This is IC, the collector current. This is IB, the base current, and this is IE, the emitter current. So if my input signal was a sinusoid, let me draw it here. Let's say it's 1 volt peak to peak, something like this. So this is 1 volt plus 1 volt minus 1 volt. This is the Vin. What is going to be my output? This is Vin out. Let's draw this as my input voltage, and let's assume that my VCC is somewhere here. This is my VCC. Okay. Right, what is my output? We don't know. We have to find it. So what we know about this is that if this transistor, BJT transistor, is in cutoff, if in cutoff, then IB is equal to 0, no current in the base as well as no current in the collector. I say 0. Because of that, the voltage across this resistor, which is IC times RC, IC times RE, because IC is 0, the drop across this is 0, So therefore my voltage V out should be equal to VCC minus ICRC is equal to VCC. So whenever this transistor in cutoff, my output is VCC. Okay, the next case is if we don't know when it is cut off, we have to find out. Next, if in active linear region, active linear mode, then we know that IB is greater than 0, IC which is equal to beta times IB which is also greater than 0, and from the above same equation V out is equal to VCC minus ICRC. Yes, I have it wrong, so let me see. So ICRC. Now this time IC is not 0, so is equal to VCC minus beta IB times RC. What is IB? To find IB, we can apply Kirchhoff's voltage law to base emitter circuit. So what is base emitter circuit? This circuit here. This circuit right here. Okay. So in order to find that, we know we have voltages here. V in, a voltage drop across the base resistor RB and VBE. So we can write the Kirchhoff's voltage law. V in is equal to IB RB plus VBE. That is actually 0.7. Okay. So what is IB? V in minus VBE over RB, which is equal to V in minus 0.7 divided by RB, and anytime this V in is less than 0.7, this quantity will be negative. But of course IB cannot be negative across the VE junction, which means anytime V in is less than 0.7, my diode will be in cutoff, which means when V in is less than 0.7, my output will be VCC. So this is when I want, this is 0.7, let's say it's around here, 0.7, this is 1, so this is 1, this is 0.7, so whenever my signal is below that, let's write this, all throughout this, my output is actually equal to this value. So that's my output from here to here, here to here. It will be like that. So let me use a different color for this. Brown. Okay, so it will be like that. During this other times we don't know. We have to find out. Okay, so V out then is equal to okay, when V in and cut off, and then therefore V out is equal to VCC. V in greater than 0.7 means that it is not in cutoff, it is conducting. It may actually be in saturation also, or active linear region. Let's assume it is in active linear region. So V out can be written as this. So V out is equal to VCC minus IC is beta times IB, taking from the previous result, is V in minus 0.7 divided by RB times RC. So we have is equal to V out is equal to VCC minus, let me take this term first, beta RC over RB times 0.7, so minus minus, this is positive, let's put this in brackets, minus beta RC over RB times V in. So this part what you have here is a constant. VCC is a constant. Just the battery voltage, beta is a constant, let me maybe underdo something. RC and RB are also constant, 0.7 is a constant, so this is a constant. And that value of constant is equal to this expression, and my output voltage is equal to this whole expression, where this one is always positive. So therefore you have a constant minus a positive value. What is this value? When V in is equal to 0.7, this term is exactly the same as this term. So beta RC over RB times 0.7, both same. So therefore my output will be at 0.7 if V in is equal to 0.7. V out is equal to VCC. But as V in increases, what happens to V out? It gets something gets subtracted from a constant. Okay, so V out actually reduces. So therefore, and it is, the shape is actually very similar to V in. It changes like the V in. So it is sinusoid, but it's a negative. It's just negative. So what you will see is my output will, this, as this goes up, this goes down like that. So this is my output. So what I would see is, when I input a sinusoidal, I would see something like this. This is a sinusoid. No, it is not. Certainly not. So therefore, what I get is not a sinusoidal signal. This is not acceptable. We see that more than half of the signal is cut off if I apply a sinusoid signal to a transistor. To avoid this problem, we use biasing. This is why we need to bias. So what is biasing? Right, so let me just give a couple of sentences before I move on. Therefore, more than one half of the signal is cut off. In order to get the full signal, we need to make sure this input never goes below V gamma, no, 0.7. But do we have control over the input voltage? No. So therefore, since we cannot always control the input voltage, what we do is we apply a fixed DC voltage at the base of the BJT to keep the transistor in active linear region. In active linear region, even when the BJT, sorry, when the input is negative. So for example, the input can go, let's say, up to -2. Then in order to ensure that my transistor never goes to cutoff, I need to add how much? If it went to 0, you have to add 0.7. So if it went to -2, then you have to add plus 2.7 at least. So this is called biasing. This is called biasing.